Good morning, good afternoon, or good evening, depending on where you're joining us from in the world today, and welcome to the latest webinar in our new Game Developer Talk series, Investigating and Dispelling Shader Myths with Science, presented by Matt Ozdele. I'm Alyssa McAloon, a publisher at GameDeveloper.com, and I will be your moderator today. We have just a few announcements before we begin here today. Today's presentation is designed to be interactive. You'll see a chat bubble on the upper right portion of your window where you can interact with your fellow attendees during the presentation. A live Q&A will follow today's talk, and to submit a question either in text or ask live on video, please click the button found right below the video window to go through that process and submit your question. Lastly, if you're experiencing any technical problems, please click on the help widget found at the bottom of your screen. So now on to today's presentation, Investigating and Dispelling Shader Myths with Science. Discussing today's topic is Epic Games Developer Relations Technical Artist Matt Ozdele. With that, I will hand things over to Matt.
Thanks, Alyssa. I will not repeat the title of this talk, but the subtitle is Shining a Light into the Dark Areas of Math with Art, because at the end of the day, shaders are just math that make art, and I think that's really interesting. So yeah, let's talk about shader myths. These are ideas that we've all got in our heads about how shaders work, how we're supposed to write them, and I thought it'd be a good idea to dig into some of those to see just how valid they are and dispel some of the pernicious ones and confirm the real ones. A little bit about myself. It's been about 11 years since I started working in the games industry, and before starting at Epic, I worked on over a dozen projects across 6 different game engines, with 2 or 3 either tangentially or in prototype. And through all of that, I supported and enabled art and design teams to do their best work. And about 3 years ago, I joined Epic Games as a developer relations technical art, where I get to empower all of the users of the Unreal Engine to push the boundaries of the technology through education, exploration, advocacy. Of course, to start every project, you must begin with good research, and I gathered a number of these myths, dogmas, and best practices from former colleagues, my current colleagues at Games, and the wonderful community at tech-artist.org. And I want to give them all a big thank you for their contributions. And I selected a few of them. We're somewhat grouped together and engine agnostic, and I'll go into the details of each of these as we get into them. But to give you an idea of what we're up against today, firstly, the myth that instruction count is equivalent to performance, is the measure of performance. Secondly, the myth that multiply is more performant than divide. And thirdly, that the cost of the POW node is exponential. Fourthly, that it is better to and faster to pack individual floats into vectors before performing math operations. Fifthly, that bigger textures are more expensive to sample. Sixthly, that it's better to use lookup tables in performing complex math operations. And finally, that it's better to do complex operations instead of using lookup tables. But there's some big questions to get started. Why are we here? What's the point? Who is this all for? Why is this guy giving this talk? And I will answer out of order. I am a technical artist. I am not a rendering or graphics engineer. I have friends who are, and they are lovely and helpful people. I am not one of them. This is going to be less Scientific American and more Mythbusters. And to answer the rest of the questions, this is for those of you who are interested in shader performance optimization. Even though modern graphics hardware and processes make it possible to throw quite a bit at the wall and still end up at a 60 FPS game, sometimes you want to find the low-hanging fruit, or you need to use the last few microseconds out of your landscape material to make sure that everything fits into your frame budget. Of course, the next big question is, how are we going to measure and test all of these things? And that's a great question I'd love to tell you, because in order to do that, we have to tackle the first big myth, that instruction count is a good measure of performance. This is perhaps the most pernicious myth in shader and material development. And it's tough because in the Unreal Engine, for example, we show the instruction count for your material in quite a few places. We've even had support for showing specific platform stats and include the instruction counts broken down by vertex shader and pixel shader at all different quality levels, along with all the number of texture fetches and samples. It's all good stuff. Unfortunately, these don't tell the whole story. HLSL instructions are just one part of a larger pipeline to get what you want showing up on the screen. So as a very brief overview of what happens, you first take your material graph, turn that into HLSL, then there's a compiler that turns that into HLSL, and then takes that and turns it into a sort of generalized assembly. And then you take your specific graphics card, and that turns the generalized assembly into hardware-specific bytecode that actually gets executed on the GPU. So keep in mind that GPUs don't really like to backtrack. They like to run one set of instructions straight through, and that's what ends up in the bytecode. However, not all HLS instructions compile out to the same number of bytecode operations or cycles. As my friend Ben Clower discusses in his two-part series on YouTube, Shader Performance Basics, he shows how one HLS instruction, for example, hyperbolic t, compiles out to something like 64 cycles of shader bytecode. I highly encourage you to go check out that video series for a deeper dive into the topic. It does a great job of explaining this. This talk is largely meant to build on that series. You can think of shaders like a recipe. You might have a recipe for cookies that has 6 steps and is done in an hour, or you might have a recipe for beef bourguignon that's 6 steps and takes 6 hours. And that's largely because when you break down each step into its constituent parts, you start to see that each quote-unquote step may take more or less time or require more context switching. Each of these steps is not an equal amount of time. They're not equivalent or interchangeable. You have to sometimes parse them out into individual actions, like if you were writing it for a robot. I don't know about you, but it takes me less time to dice an onion than it would a toddler, but it takes a toddler and I the same amount of time to pour oil into a Dutch oven. And not to belabor the point too much, sometimes an instruction is as simple as draw some circles. And sometimes an instruction is as complex as draw the rest of the dang owl. So it's not instruction counts, then how are we going to compare these myths? Well, I mentioned earlier that what really matters at the end of the day is how many frames you can render in a second, right? So that's how we're going to measure these. And to get things started, we're going to use the currently in preview Unreal Engine 5.1. Every myth is going to be tested with a full screen material. It's going to take up the whole screen. The only thing that is affecting the base pass cost of the frame is that material. And this isn't an exhaustive survey. Again, this is Mythbusters, not Scientific American. I'm testing this at 1920 by 1200 on an A6000 RTX graphics card. So I will, of course, caveat that different graphics hardware platforms and so on will provide different results. What's important for this test is that all of the results in all of the tests were done with the same hardware at the same resolution. And finally, to gather all of this information, I used our built-in tool called Unreal Insights to gather timing data about the GPU, and we'll use that as the basis for our evaluation. But the timings coming out of Unreal Insights aren't going to be frames per second. It's going to tell us how long it took a frame to render. That's just a raw milliseconds value. I generally dislike using frames per second as a basis of comparison because the difference in how long a frame is depends on how many were rendered in a second. So if I tell you that we got 5 frames back, that means something different if we went from 55 FPS to 60 FPS. That's 2 milliseconds. But the difference from 25 FPS to 30 FPS is almost 7 milliseconds. That's a big difference. That's a lot of stuff that had to change in order to make that difference. So that's why I don't like using frames. I much prefer to use milliseconds. So from here on out, it's only milliseconds. So let's talk about the materials that we use to test these myths. I am, of course, using Unreal Engine's super powerful node-based material editor. That's where all of this is going to happen. The material editor also has a custom node that lets you inject arbitrary HLS straight into a compiled shader, which is what we leveraged, which is what I leveraged very heavily in order to take care of all these tests. So each material is going to be unlit. It's going to be opaque to minimize the outside influence on how long everything took to render. And most of these examples will use custom expressions with parameters inputs and a for loop with a brackets loop specifier around it. I'll get to that in a second. I really needed to hammer the GPU on this one. Some of these operations don't take a lot of time at all. I have a very powerful graphics card. So instead of doing 1 multiply per pixel, I needed to do 1,000 multiplies per pixel. And that's where the custom expression came in. And that's where the for loops come in. Because if you've ever tried to profile something in Python, you might have done something like this. Import time, get the time before your operation, do your operation, get the time at the end, and print the difference. But the difference is going to be so small doing simple operations like this on modern CPUs, you might not even notice the difference. How you know your code, it was your code versus a butterfly versus a solar flare. There's so much that can go into just very, very minuscule timing. So instead, you do the same operation a bunch of times, and then you can start to see either extant or significant differences between two possibilities. So the other thing that I tested was using custom expressions versus using our built-in nodes, using the loop specifier or parameters or constants or stuff defined in the custom expressions. And part of this is because, again, so much of modern GPUs and graphics hardware and processors is made to optimize for you. And I wanted to unoptimize everything. I wanted to get the worst case scenario for all of these tests. So I didn't want the GPU to do any of that work for me. So what I found in testing is that the loop specifier and using Unreal Engine's parameter nodes as inputs to the custom expression gave me kind of the worst case scenario results. So we'll be going with that. So just to talk about bringing it back to the instruction count myth, we're going to do two different operations. We're going to do a multiply and an arctangent 2, and we'll loop that 1024 times per pixel with that loop modifier, and we'll check out the results. So once we crunch the numbers, we see that there's a mere 15 difference between the two operations, arctan2 and multiply. And we get very different base pass timings for these two different materials. So 15 instructions does not equal 2 milliseconds in this case. And that's because if we go back to the shader bytecode, arctan2 ends up something like 120 cycles to do a single float for certain byte compilers, whereas multiply is 4 cycles, give or take. And that leads us into the second myth, which is multiply, don't divide. I've always sort of understood that dividing in a material is a more expensive operation than division, but I never really questioned that assumption. I'm guilty of this myself. I wrote a material that took a degrees input from camera's FOV, and I needed to convert that to radians before doing any sort of trigonometry on it. And since the trig operations in Unreal's material system use a period of 1 by default, that means 1 radian is 1 degree, or the reciprocal of 360, or 0.0027 repeating. And because I always understood that divide was more expensive than multiply, I multiplied my degrees value by that sort of nonsensical 0.277 repeating number, instead of just dividing it by 360, which would have been more readable and legible. But why do we think this, though? And I think if you go back to grade school arithmetic, you might remember multiplication is just a series of additions, whereas division is a recursive series of subtractions with conditional statements and extra variables you have to keep track of. And again, GPUs they just want to go straight through. They don't want to have to do a bunch of stuff. They don't want to have to loop back on themselves. So the tests are going to start looking really familiar from here on out. Same thing as instruction count. We're going to accumulate the results of A divided by B and A times B into a float and just output that from the custom expression. And same as before, we'll do that a lot and compare the results. But these results are pretty close, right? It's not nearly as bad as I would have expected for something like this, for as much as I had internalized divide, don't divide, always multiply. And I took a look at that. And so we go into the bytecode. So I used Tim Jones's shader playground. If you haven't checked that out, it's really interesting to see how HLSL gets turned into different bytecodes. And instead of doing any sort of recursion or additional operations, what's actually happening here is that first bytecode operation gets the reciprocal of the dividend, and then the second operation is multiplying the divisor by that reciprocal. So any sort of divide operation is just going to be a quick reciprocal and then a multiply, and then you still get your division out the other end. So it's a little more expensive because it's now 2 operations, which is kind of what we see over here, but it's not dramatically more expensive. But speaking of things that happen in bytecode and how our brains do with math, another sort of common understanding is that the cost of a POW operation, raising x to the y power, rises exponentially based on the exponent of the operation. And this sort of makes sense, right? Because if you're given a limited series of bytecode operations, then it stands to reason that to raise a value to a power, you would need to multiply it that many times. So I might take my little POW, 2 to the 8th power, and my first bytecode, I'll move 2 into the first register, and then I will multiply the first register by itself and put it in the second register, and then I'll multiply the first register by the second register 7 more times in order to get my 2 to the 8th, right? So this test, same thing, we just loop 1024 times and tested different exponents using material instances. So we do 4, 8, 16, 32, and so on and so forth. But if you look at the timings for this, it gets a little interesting because they're the same number. And that's really, really quite strange to me, especially with the variability of GUs. The average values here were the same. And so if we graph that out, we do start to see a sort of exponential curve. But it really just sort of steps at a couple of points. And then once we get to the 64th power, it sort of flattens out, right? And true exponential graphs are asymptotal. They don't ever flatten out. They only flatten out at infinity, but this is like dead flat. So what's happening here? Digging into the bytecode, we can start to see how all of this really shakes out. So running a few different exponents through the POW operation and inspecting the resulting assembly in the shader playground, the first 3 powers all track with what I'd expect. It's a little more clever than what I was doing. So to raise something to the second power, you just multiply by itself. And then to raise something to the 4th power, you just multiply it by itself twice. Hadn't thought to do that. Very clever. And then to raise it to the 8th power, you just multiply it by itself 3 times. Again, very clever. That's fewer operations than I was taking. But then we get to the 16th power, and this is where it gets interesting. So instead of multiplying it by itself yet a 4th time, instead it employs this sort of mathematical trick for exponentiation, where it gets the log of the base and then multiplies the log of the base by the exponent, and then raises e to that power. And this works for every exponent. You can very quickly calculate the power operation using these 3 instructions, these 3 bytecode operations, in a fixed number of cycles, as opposed to having to do a bunch of recursive multiplication, which I think is really clever. And so to sum this one up, exponents do rise in cost to a certain point. But beyond that, then again, the GPUs try and do a bunch of work for us. They employ a bunch of clever tricks to make it easier to do these sort of operations. And so one of the other clever tricks that I thought GPUs employed was they would pack floats together in order to multiply them together. So this one kind of goes back quite a ways, but the basic idea is that GPUs at a certain point all just did vector operations. Everything was vec4, and so if you were multiplying 2 floats together, it was really vec4 with one channel and vec4 with the other channel. So it would stand to reason that it would make more sense to pack both sides of your multiplication into vector 4s and then perform the operation because you're already doing it anyways, right? I know for a fact that I have done this quite recently in the name of optimization. It was part of a broader optimization initiative, and I didn't really take the time to think about how that specific optimization was affecting overall shader performance. As with so many of these myths, it's something that I had heard or had always done, so of course I did it. The way it worked was there were 3 pan UV values, but only one channel was used for each. So over here you can see we've got our speeds, and then we append 0 to the speeds. We pipe that into the panner node, and then we're panning our UV values, and then we'll sample 3 textures. We'll get to that later. So this seemed a little inefficient to me because we're panning a bunch of extra values here that we don't really care about. So instead, I packed those 3 float speed values together, multiplied them by time, got the fractional value for accuracy's sake, and then added them to the offset. So this was really dead simple panner operation. And I thought that would work, right? Because yeah, like I said, on the one side of the operation, you've got just a plus b, But then on the GPU, it might be float 4, A000, B000, and then add those together. So really you're adding a bunch of, or multiplying a bunch of extra floats that you don't really need to. So to test this, I started with 24 scalar parameters input into a custom expression, and then I multiplied the first two together and add that to the out accumulator and the second two, and so on and so on and so on. And then for float 2, I pre-append A and B and C and D, and then I multiply AB times C and so on. And then for float 3s, I would append together ABC and then multiply that with DEF. And finally, for float 4s, I append ABCD and multiply that with EFG and so on and so forth. I felt it was fair to handle the append operands outside of the custom expression, since we only need to do that once, and I didn't think it was necessarily fair to the comparison tests to have to do the append 1,024 times. That is something I would be happy to discuss and modify this test. I think there's a bunch of different ways you could have done this. But at the end of the day, in theory, each of these tests is multiplying the same number of floats together under the hood. It's always 24 floats, and it just sort of broke down mathematically that you do 12 multiplications for floats and then 6 multiplications for float 2s, 4 for float 3s, and 3 for float 4s. So in theory, this is all the same amount of multiplication. But here's where it gets kind of interesting for me. Once again, the number of instructions goes down for each of these tests, but the base past millisecond cost doesn't quite track with that. So it would seem to me that this myth might hold some water for float 2s, but not necessarily for floats. So it might be the case that certain GPUs, maybe mine, can handle individual float operations and float 4 operations, which would mean that the 12 multiplications we're doing here are actually 12 float 4 multiplications, or 4 float 3 multiplications, and only 3 float 4 multiplications. So it could be we are indeed doing extra work here that we don't need to. The takeaway here is that in certain circumstances, if you've got a couple of floats that you need to do math operations on, it might be faster to just do the float multiplication instead of trying to pack everything together. Taking a brief detour from math for a second, let's talk about big textures. This one I think is fairly common, and part of the reason that we don't use big textures everywhere aside from memory is that it takes more time on the GPU to sample a larger texture than a smaller one. This is what I've always understood. And I've lied on this assumption in the past. I put this into production. I was working on a title, we were getting down to the wire, and we need to eke out we were trying to pull every trick out of the book to get just a few milliseconds back here and there. And so I went over a bunch of materials and textures with one of my environment artists, and we highlighted a few like 2K normal maps. Like there was one 4K detail map or macro normal map that was being used in a material that was used everywhere. So I knew it was any changes to that material should show up and lower the resolution of those textures because big textures are more expensive to sample, right? So why? Why do we think this is kind of interesting? So we leave out memory overhead, and we leave out the overhead of texture streaming. And so let's just focus on the work the GPU needs to do to sample a pixel. So when you've got a UV coordinate, that's a float, a 32-bit floating point, and or maybe 16, depending on your hardware. But the precision of that UV coordinate is much greater than any texture you could possibly come up with. So you need a way to filter that sample. And so the first method for filtering that sample is nearest. You just find the pixel that is nearest to the coordinate and you return it. This is how you get some fairly pixelated results out of your textures, though, which may or may not be desirable depending on your use case. Now, the more common method for sampling a texture is called bilinear, where you take 2 pixels on either side, or 2 columns of pixels to the left and right of the one that you select. You lerp those together, and then you lerp those 2 lerps together. That's how you get bilinear filtering. It's really useful for sampling kind of 4 adjacent pixels and getting a roughly correct value for whatever UV coordinate you're sampling. And then the third is trilinear filtering. It's same as bilinear, but it does additional interpolation of bilinear results with the MIPS on either side of your current MIP. So it would stand to reason that it takes a bit more time to look up and filter based on the size of the texture we're looking up. There's more to interpolate, there's more pixels to figure out that we are or are not close to hitting, right? So same as before, we're going to test the heck out of this. So I started with a 1 pixel texture, then a 2, 4, and so on, all the way up to 8192. I clamped the sample for each of these texture samples to MIP zeros. I wanted to see, hey, we're sampling an 8K texture. How expensive is it to sample an 8K texture? I don't care if it's a 4K texture at the MIP that I'm actually seeing at. And of course, we tested all of the different filtering. And this is, another interesting graph. The results were interesting to me. So the bilinear sampling line tracks about what I'd expect all the way up to 1024. And then bilinear filtering, because it's the default in Unreal, that's my assumption. That mess with my assumptions. Nearest filtering was a little bit of a fluctuation, but that trend line is basically flat. And then trilinear filtering was this really interesting one to me because it's got that hump there, but then it flattens out at 1024, just like nearest and bilinear. Now, looking at test setup and having a better understanding of filtering, it's distinctly possible that the method I was using to clamp the MIP level here was inadequate, and the GPU was already sampling that just the 1024 MIP for textures beyond that value, which is why everything flattened out. There's definitely some future work there. Follow me on Twitter for more updates to that one. So speaking of textures, let's talk about using lookup tables instead of doing math. So this one is all about trade-offs. The myth here is that math is expensive to do on the GPU, so you should just use texture fetches instead. You can pre-compute your results of complex math operations like sine, cosine, tangent, and drop those values into a texture that you can look up instead. Why might that be? Why might we think this? Well, at one point or another, the people who were writing shaders were trying desperately to conserve instructions and cycles. It seems like with every generation of hardware, there's always a trade-off between memory and GPU time, and at a certain point, it was cheaper to memory was cheaper than GPU cycles, and so we were trying to save cycles. So it's easier to just hit the GPU with a really quick small texture fetch than it was to compute whatever math you needed to every frame. So for this test, I used the Unreal Engine's curve atlases to create lookup tables effectively for sine, cosine, tangent, arc, cosine, arc, tangent, and so on. And I squished those values between 0 to 1 to keep them within the bounds of the atlas. And then curve atlases in Unreal just bake down to a texture at runtime, so you can just sample these as textures and look that up based on your desired curve, which is your column, and the time along the curve from 0 to 1, which is row. And I made 4 different curve atlases for this with same inputs. So 90 pixels wide, 180 pixels, 360, and 720. The pixel size basically represents the accuracy of our lookup table. So on the low end, we have a sine curve that's 90 steps with a sort of bilinear filtering between those 2 steps, so on and so forth. And then the other nice thing with curve atlases in Unreal, you can specify non-square resolution. So we're looking at a 6 by 90, a 6 by 80 texture, and so on and so forth. So once we get that into the material, we just sum the values of the LUT at each step of accuracy for each step of accuracy. So if the input curve is 90 pixels wide, we'll do 90 samples. And if the input curve is 180 pixels wide, we'll do 180 samples. And on the math of things, we'll do the same thing, but instead of sampling the lookup table, we'll just perform the pure math operation. And just for safety, because arc-trig operations require a certain value range, saturate the value so that it stays between 0 and 1. Because saturate is free, right? That one didn't make it onto the boat. Gonna have to follow up on that one. So then let's look at the results of this test. It would seem to be that at all step levels, sampling the lookup table ended up being more expensive than the equivalent math operation, right? So it was a little more expensive at 90 steps, and then that cost grows and grows and grows and grows. But that said, I do think there is some room to find the inflection point at perhaps a lower level accuracy. So maybe you only want a 30 pixel wide lookup table for your sine table. You don't need a super accurate sine table. That might work for you. I got to find that inflection point. So that's more homework for me. So the flip side of that myth is that it's better to use lookup tables for certain or it's better to use math for certain operations than to use lookup tables. Texture fetches are expensive, so just let the GPU rip through the math, since those are so good with math, right? This is also a thing that I get to show a sort of real world example of. Remember that panning operation from before? So the input or the output of those panners going in these three 512 by 512 noise textures, but it was only sampling 1 pixel wide. It clamped down so that it was only sampling 1 pixel across. But now we're sampling a 512 texture and only using 1 pixel's worth of that. That seems pretty expensive, right? And because it's this creating this kind of panning noise texture across itself, we needed these 3 separate samples for creating those 3 separate panning noises. Again, this felt very expensive to me. So instead, I created a function that creates a noisy curve, and then I can sample that curve at a bunch of arbitrary points, and it gives me an infinite amount of accuracy. So I replaced each of those texture samples with just this little bit of math that uses sine and cosine and a smooth step to create this curve. And I will have a link for this available as well. I think it's really interesting. So what that let me do is replace those texture samples with these 3 noise samples. And that ended up being less expensive within the broader context of that material. But you'll also notice that I break out, here's my quick panner, and then I break that out and I do these 3 noise samples, and then I pack them all together. So part of the reason is that within the noise function itself, I packed 2 values into a float 2 and then did math on it, because I thought that saved instructions. That was something I had always believed. Turns out I was wrong, as I have now learned. So I tweaked how that noise function worked, removed that extra texture pack, and what that let me do is switch it so that it was only 1 noise sample function. And then I could break out the components of that. So it's doing the same stuff on each of the channels. It's just doing it in this 1 call instead of 3. And that reduced the instruction of this test from 2,203 to 926. Now, I know that I said earlier that instruction counts aren't everything, but they're not nothing. So in the first test with that individual channel noise sample, we can see that was indeed more expensive. And with that vast difference in instruction count, hey, maybe that's not necessarily surprising. But the math version was more expensive to render, and so I did that, and that's when I'll write vector pack, and I was doing that. And so I ran another test with a new streamlined material graph, and that did save quite a bit of time in addition to instructions, but it ended up being just a hair slower than the results from the texture. And I'm trying to prove a point here, so I removed the smooth step from that math operation. I was able to get it down to just below the texture operation. So I felt pretty good about that. Managed to speed things up. Smooth step is fairly expensive, and maybe the noise texture wasn't smooth step. Maybe I didn't need it. So this was all very interesting to me. So what have we learned today? Well, based on the test results from our various myths, it seems safer asterisk to say that possibly instruction counts are a tool in your tool belt for diagnosing performance problems, but they shouldn't be the only tool. It turns out that divide is in fact maybe a little more expensive than multiply. We did learn that the cost of exponents does in fact increase. To a certain extent, the bytecode compiler optimizes it down to a more efficient method. Vector packing was a bit of a surprise. Turns out it might be better to just let floats be floats, but packing float twos together to do math on them was maybe not as cheap as we thought. We also learned that hey, texture size sampling, that I'm just going to call that confirmed, that met my expectations. And then at a certain scale, it seems like it's better to do math than to just use lookup tables. But at the same time, it also might be better to use lookup tables than to just math. Because in conclusion, it depends. It depends on resolution, it depends on hardware, on compilers, on engines, on your test conditions, on everything else that's happening, the material, everything else that's happening in the frame and wave occupancy, and all of this other stuff that goes into GPUs. So was this an exhaustive and fully scientific survey? No, not really. But this gives you some insights into some things that you can do to optimize the performance of your materials. And if nothing else, what I hope that you take away from this is that when in doubt, test in isolation with a repeated number of operations in a consistent manner. I don't know about y'all, but I have homework to do from this. I know there's still a bunch of tests that I want to do. I want to do finer grained exponents using non-power of 2 values, using non-integer values. I want to find the inflection point between lookup tables and trig at lower sample counts. I also want to compare lower resolution trig operations using higher step levels. So if you wanted to get, a fractional value on the 90 pixel sine curve, what does that look like? Obviously, I need to test on more hardware and platforms. And I also need to design a more robust test for trilinear texture filtering. I will probably, hopefully, be posting a bunch of follow-ups to this on Twitter. So feel free to follow me and I'll post those updates. Finally, before we wrap up and move on to Q&A, I wanted to thank all of the folks that helped make this possible. Firstly, my colleagues at Epic Games and the folks at tech-artists.org who helped me brainstorm the myths for this talk. Secondly, I feel like I can't do a materials talk without thanking Ben Cloward for his inspiration and background work. And thirdly, and specifically, my colleague Sebastian Tomacek, whose contributions to Unreal Insights made it possible for me to conduct all of these tests really quickly. And lastly, the folks at GameDeveloper.com and Forma who gave me this opportunity and put the whole show on. I'm ever grateful for the chance to present on such a special stage. And with that, I believe it's time for questions. And if we don't end up having time to get to your questions, feel free to reach out to me on Twitter. If you have any ideas for myths or something that I might have missed, please let me know. I would love to keep digging into things like this. Thank you.
My first question was actually going to be, hey, what's your Twitter handle? So I'm glad you got that up on the slide there. Thank you so much, Matt, for that presentation. And then for the audience today, before we move on to the Q&A, we will have a networking session after where you can kind of talk amongst yourselves about all your own shader hacks and your own shader myths that you want to unpack. So be sure to stick around for that. But before we move on to the Q&A portion, I do want to highlight the survey link that we will be sharing in chat. Please take a moment to share your thoughts on our Game Developer Talks webcast, and your feedback is key to helping us improve future events. So we're really looking forward to hearing from you. So all that said and done, now on to the question and answer portion of our event. As a reminder, to participate in the Q&A, just click the button below your presentation window right there and either type your question into the text box or join the line to ask your question on camera. And as mentioned before, be sure to stick around after today's live Q&A for our interactive networking session as well. So I got a mouthful of things to get through here. So with that, we'll just jump into some questions. I think just good one to start off with. Out of all the myths that you've kind of unpacked here or ones that you've done just throughout your career, what's the kind of like one big myth, one quick trick that's made the most difference for how you work that you've unpacked?
Ooh, so there was that that material I was optimizing earlier, and that being a few tricks. And one of the myths that I didn't get into that I employed heavily on that one was the if node in Unreal is somewhat contentious. because so again, GPUs don't like to have to backtrack or do conditional stuff. So there is the thinking in the theory that the if node, which in Unreal compiles down to a ternary operator, it isn't a proper like GPU dynamic branch. The theory goes that both sides of your equation end up getting calculated. So if you have like, if A is less than B, do this, or if B is less than B is greater than A, do other thing. And the thing goes that thing and other thing will both get evaluated. And there was a user on Twitter a couple of years ago, and I really, really wish I still had that bookmarked. And she had started to do this similar with like looking at the GPU timings, using an if node and a bunch of expensive operations. I wish I had gotten to dig into that. So that's one I didn't get to. I want to do a little bit more digging on that one. In the context of that material, it did end up saving a bunch of time because it was optimizing away, or it was cutting away some texture. So the way it was currently working was lerp between two things based on a vertex color. And with a lerp, definitely both sides of that are being evaluated. There's not an optimization that's just going to cull one side of the lerp because the input into a lerp is dynamic. So I replaced all of those lerps with an if node, and I did see savings. That one was one that was really helpful, and I want to do a little bit more research into to say definitively how and why that one is the most helpful.
Mm-hmm. This is going to segue into a personal question, I guess, not personal, but like it's something I'm really interested in. Game developer ran an article like ages ago that's like dirty coding tricks, dirty game development tricks that are always these tiny little things that you would be surprised. It's kind of like the Olive Crash Bandicoot when he dies shrinking into the shoe kind of situation.
Oh yeah,
So
yeah.
what's the shader version of that, I guess? What's the kind of like one
Ooh.
surprising trick that like people might not realize is going on, but like everyone with shader know how? It's like I
Mm.
recognize that.
Um. So I think, oh man, one of the like dirty shader tricks.
It's
I
a
think
little bit of a tangent, but like I'm interested
yeah.
after you started
No,
talking
no, no,
about it a
no.
little
That's
bit.
a good one. Like I do this all the time. So I think one of the ones that I think is a lot of fun that I didn't understand when I was a student, when I was just starting out with materials, is the power of the UV coordinate node. So the UV coordinate node gives you a 32-bit gradient from 0 to 1 in directions. And
Mhm.
you can reduce your texture fetches. So if you want, a gradient from left to right, you can just use the UV coordinate node to get that instead of using a texture to get the gradient. So that I think is a really fun dirty shader trick a lot of people employ. I know in Unreal Engine we have a bunch of material functions to create different gradients that are all based on the texture coordinate node. So if you want to do, and you can do some really trick stuff with it. You can do circular gradients. You can use it to do sort of sign distance field. I know
Mhm.
one of my colleagues at JoyRock on Twitter, she uses a lot of it for doing sign distance field and some really interesting stuff in UI materials. So yeah, texture coordinates instead of using texture gradients. It's a lot of fun.
That was a life hack. Great. Appreciate it. I feel like my
Mhm.
segues here might show that I'm a newbie on the math side of things. I was an English major in college, so you like started talking formulas, and I'm just like, cool, that sounds great. So
I
I
mean,
apologize. My segues aren't going to be super great, but
that's okay. I went to art college. I explicitly didn't take calculus in high school because I was going to go do art for video games, and then I fell into technical art, and now I'm doing math again. So
one of my kind of like half joking questions I was brainstorming on the way was like, how do you get artists to care about math? Which seems like an entire talk on its own, right? Especially going to art school.
yes, and that was a fun one. So part of the reason I started to get into and started to care more about math was because of materials, because of the work I was doing to create different texture effects and kind of exploring that. And I think again, I know he gets a little embarrassed every time I call him out, but Ben Cloward's shader talks from GDC 2016, 17, and 18 he really breaks down like, hey, here's this really cool effect that you can do with this little bit of math, and then he does a really good job of building on it. And I think that that really helped spark my interest, and push it forward. And nowadays, I think the other thing, when I started out, there wasn't a lot of math that was exposed or available to me. I wasn't a rigger. I was mostly doing materials, and at the time I started out, it was UDK. Actually, even before UDK, the Unreal Development Kit, so Unreal Tournament 3 modding effectively. I wasn't scripting, I wasn't coding anything, so I wasn't exposed to that side of things. But then as I sort of progressed through my career, I got exposed to vector math and linear algebra. And it's like, oh, I can do some really cool stuff with linear algebra that I didn't think was possible. And then it's like, oh, well, if I can do, dot product and then project a point forward and then do, plane line intersections and do some really interesting stuff that, yeah, I think it was really just like slowly but surely working my way and falling my way into more and more complex shaders and trying to do more and more complexness with them that got me into more math. But that said, I'm certainly not a mathematician by any stretch.
Could have fooled me, I think. And I will say, for the audience's benefit, we do have the resource tab on the left side of your screen. I should have mentioned earlier that has some GDC talks in there, have some GameDeveloper.com articles talking about just like everything shaders and that entire world you can dive into. So reminded me to bring that one up there. And talking, I guess, about materials a little bit, and this is where I might show my newness to the world of tech art. We had a audience question that I'm scrolling up to get the right acronym, asking if Unreal materials are BRDFs, and I guess like best practices around using those, or how that relates.
Yeah, so with Unreal Engine 4, it's over from your sort of approximated diff norm spec to the Disney BXDF. They are all physically based rendering materials. I think that the sort of the one important thing to understand about that is that the specular, it's funny, this came up recently, so I was already planning for this. And then, so one of the big things is that you still have the specular input pin on the material input node, and that in a true physically based rendering world, you shouldn't touch that like at all. But sometimes you will need to art direct to change the shape of your specular lobe, and that's what that's for. You don't necessarily need a specular map for everything that you're doing, because generally speaking, roughness and metallic maps will handle properly shaping your specular lobe based on those inputs. So if you have a really rough metallic material, that's going to look a lot different than a shiny dielectric material. And generally speaking, the physically based rendering will handle all of the stuff that you need to for specular. I hope that answered your question.
I'll defer to the audience member there because I had to look up the acronym. So I think last question here is just when it comes to myth busting and like tearing apart these and identifying the myths that you want to dig into, I guess what's your kind of broad advice for technical artists who, after hearing you talk today, are like, I want to put my own knowledge to the test. I want to like tear apart my own myths. What are your kind of like, here's how to do this with your own work advice for them?
Yeah, so I didn't really get super deep into the sort of test rig for this. And I will probably end up doing a YouTube video on that at a later date, but also Ben Cloward's Shader Performance Basics series, he gets into that as well. And the sort of basic idea is you just need a really simple scene with a big plane in front of a camera and maybe one light and one unlit emissive material, and then average GPU timings. And you can do that. You can just use stat GPU in Unreal to kind of get a rough estimate, or you can use Unreal Insights to gather that full GPU timing data. I go into how to do that in another series on the Quixel YouTube channel that I did a while back. But yeah, I think the important thing is, like, if you're doing these tests, do it in a packaged build to get proper results, because the editor is going to have a bunch of extra overhead that may be affecting your values. Make sure you're doing it at a consistent resolution. So for all of these tests, Actually used Unreal Engine's Gauntlet automation system to cycle through a bunch of different materials and get the timings, and then output those timings into a CSV so that it was even in the same run instance, the same compiled executable of Unreal. There wasn't any additional work happening there. So again, consistency is key, I think is kind of the last one.
Sounds great. And we got a feedback from the audience that you did answer their question excellently the first time, so we're all good.
Cool.
So Matt, I really appreciate everything, like all your expertise today. So I'm going to work on transitioning over to the networking section. But yeah, a special thanks from us, Matt. Like, this talk has been incredible, and we really appreciate your time and expertise. That is all the time we have for questions today, so we are going to move towards our networking session. For the audience, this is an interactive portion of the event that allows you to share your thoughts and expertise with one another in a discussion-style format centered around 5 different topics. You can join the networking room by clicking on the button on the left-hand side of your screen that looks like 3 little icons sitting in a circle. Pick your topics and discuss from there. So I'm going to talk through my quick webinar housekeeping as everyone tabs over. So we'll see you in networking. I'm just going to keep talking here. Within the next 24 hours, anyone still around will receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may not have been able to listen to the live event. For some quick housekeeping, the webinar is copyrighted by Informa. The presentation materials are owned or copyrighted by game developer and Matt, with the individual speakers solely responsible for their content and opinions. Thank you so much, and we'll see you over in the networking session.